Welcome back to The Deep Dive. Today we're focusing on something in rail safety that, well, sometimes gets treated like a soft science. But when you ignore it, it leads straight to those huge multi-million-dollar failures we unfortunately still see.
Absolutely.
So I want to kick off with a question, maybe a provocative one, for everyone listening who works in engineering, in system safety assurance. What if the safest, most advanced rail system you design, perfect signals, great track, all the redundancy, what if it still fails? Catastrophically.
Because we forgot the person.
Exactly. Because we forgot the critical component, the human operating it.
That tension you just described, the balance between that hard technical rigor, the systems, and, well, human capability, that's really the defining challenge in modern rail safety, isn't it?
It really is.
People are complex, definitely unpredictable sometimes, but, they're also the most adaptable part of any system like this, any socio-technical system. If you ignore them, you're basically designing failure right in.
Precisely. So our mission in this deep dive is to really unpack human factors integration, or HFI.
Right.
And this isn't just, putting a comfy chair in the cab or making sure the manual's readable, though that helps.
Yeah, that's part of it, but not the core.
It's a rigorous, systematic, scientific process. It's about placing human needs and limits, cognitive, physical, organizational, right at the very center of railway system safety assurance, SSA. We're going to dissect the how and the why this discipline is just non-negotiable for preventing incidents and actually for seriously enhancing overall system performance.
And what's fascinating, I think, is how HFI moves way beyond just common sense or, subjective feelings about what works.
Yeah, it's not gut feeling.
No, it's a systematic scientific discipline.
Yeah.
It relies heavily on cognitive psychology, understanding how people make decisions under stress, for instance.
Okay.
It uses physical sciences and ergonomics to design the actual physical environment, the controls, the layout, and organizational design, too, how teams are structured, how procedures work.
So it pulls from everywhere.
It has to. For any major rail project now, HFI has to be this continuous scientific thread woven right through the entire project lifecycle, ensuring the human operator is truly an integrated part of the system design, not just tacked on at the end.
Not an afterthought. Okay, let's define it properly then. Hashtag HAG1. Defining HFI and its role in system safety assurance, SSA. So let's really nail down the definition first, especially for, the students, the early career engineers listening who might be hearing this term formally for the first time. What exactly is human factors integration?
Okay. At its core, HFI is defined as a systematic scientific process. And the key is that it embeds human considerations, cognitive, physical, organizational aspects across the entire project lifecycle.
From start to finish.
From concept right through to disposal, actually. It's all about achieving a balanced development, making sure the, let's say, technological sophistication of the system is perfectly matched with the capabilities, and just as importantly, the limitations of the humans who have to interact with it.
Right. And why is that level of integration so critical for system safety assurance, for SSA? We often hear SSA talked about mainly in terms of, hardware reliability, software integrity.
Technical stuff.
Yeah, the technical stuff. How does this sort of squishy, unpredictable human element fit into that really rigorous framework?
Well, SSA relies entirely on quantifiable, verifiable evidence. Proof that the system is safe under all foreseeable conditions.
Okay.
Now, if a system is perfectly designed technically, but the human interface, the driver's display, the control console, maybe even just the maintenance procedure, introduces a high risk of error, well, then the system is fundamentally unsafe.
Doesn't matter how good the tech is.
Exactly. Effective SSA hinges on balancing that technological design with human capabilities. So when HFI is done right, it directly reduces those human error hazards. It improves overall reliability, and crucially, the evidence that comes out of these HFI processes, it's required evidence for the overall safety case.
So you can't get certified without it.
Pretty much. You cannot secure certification for a complex system if you can't prove the human can reliably interact with the technology under all expected conditions.
Wow, okay. That immediately highlights the complexity, though. It sounds incredibly broad. You mentioned cognitive psychology, ergonomics. This needs expertise far outside traditional engineering, right?
Oh, absolutely.
What specific domains are we talking about here? What kind of experts do you need for effective HFI advice, and how do they even work together?
Yeah, the scope is definitely wide. which is why HFI is almost always a multidisciplinary team effort. You absolutely need input from several distinct areas.
Like,
Well, you've got cognitive psychologists. They specialize in understanding things like workload, attention, decision-making, especially under high stress, maybe low-frequency scenarios, emergencies.
okay.
Then you have physical scientists and ergonomists. Their focus is optimizing the physical interfaces,
Yeah.
the chairs, yes, but also the controls, the lighting, the layout of a cab or control room.
Right.
You also need organizational designers. They look at how teams are structured, shift patterns, how procedures are written and followed. That's huge. And then you have more specific technical specialists, people who are experts in human-machine interface usability, or HMI, and those who specialize in human reliability assessments, which I think we'll get into more detail on later.
Yeah, definitely want to cover that.
The real challenge, though, is making sure all these specialists have the right competency and can communicate their findings effectively. They need to translate their insights into the language of systems engineering, into requirements and risks that engineers can work with.
So HFI is essentially taking this, highly qualitative world of human behavior psychology, sociology, and forcing it through a rigorous quantitative engineering lens. Is that the core challenge?
That's a great way to put it. Precisely. We are translating things like fatigue or confusion or cognitive overload into quantifiable risk metrics and verifiable design requirements that you can actually test against.
Okay, let's unpack this integration piece further. Because, as you stressed, HFI isn't some checkbox you tick off at the end.
Definitely not.
It has to be woven in from day one through every stage. So if you're an early career engineer listening, you need to grasp where HFI fits alongside your standard systems engineering V model, for instance.
Exactly.
Can we break down this integration maybe into stages or pillars?
Yes, absolutely. And it has to start right at the conceptual stage. The first pillar, we could call it requirements development.
Okay, step one.
This is where the systems engineering team, working with HFI specialists, must derive explicit human-system interaction needs. So instead of just a vague requirement like provide a display, a robust HF requirement mandates specific things.
Like what? Give us an example.
Okay, like setting measurable limits on operator cognitive workload under defined emergency conditions, or specifying display readability metrics, font size, color contrast under different lighting conditions, ensuring they meet specific ergonomic standards, maybe ISO 9241, for example.
And crucially, those have to be measurable.
They must be measurable and verifiable later on in the process. That's key.
Right. That requirement setting feels immediately crucial. It sets the stage for the entire hazard profile, doesn't it? Which leads right into pillar two, hazard management. How does the human factor systematically feed into the hazard log or register?
It feeds in by proactively identifying human error modes very early on. We don't wait for them to pop up in testing.
How do you do that proactively?
Through structured, detailed task analyses. We literally map out every single step. An operator takes routine stuff like logging on, complex stuff like emergency responses, overriding automation.
Every click, every decision.
Pretty much.
Yeah.
And for each step, we identify potential failure points introduced by that human interaction. Could it be mode confusion, data entry errors, following a procedure incorrectly because it's poorly written? Identifying these early prevents the very costly and sometimes dangerous discovery of human-induced hazards late in the game, like during commissioning.
Okay, so requirements set, hazards identified. Then we move to the concrete stage, design development. This is where the analysis turns into something real, physical, or digital.
Correct. This is the translation phase. We take those identified human factors requirements, which came out of the hazard analysis, and translate them into actual tangible design elements.
So ergonomic cab layouts.
Exactly. Optimizing cab layouts based on anthropometric data, the science of human body measurements, designing interfaces that are intuitive, maybe error-tolerant, ensuring control placement minimizes awkward reaches or physical strain, reducing the chance of misoperation, especially during repetitive tasks or long shifts.
Got it. And then finally, the loop has to close. We need verification and validation, V&V. We have to prove that what we design actually works reliably for the human using it, not just on paper or in a simulator.
V&V is where you collect the proof, the evidence for your safety case. This involves actively testing the integration. Methods include things like usability tests, often using high-fidelity simulators that mimic the real environment. Alongside that, human reliability assessments, HRA, which we'll dig into, and of course, real-world field trials with actual operators.
And the goal of V&V.
The objective is to ensure that the system as deployed, meets those initial human factors requirements we set way back in Pillar 1. You're proving the design hasn't accidentally introduced new hazards and that it stays within acceptable limits for human error probability.
Okay. Now, for that early career professional building their portfolio, or maybe the system safety student, understanding the documentation, the paper trail, is vital. What are the essential deliverables that show rigorous HFI compliance across these 4 pillars?
Right, the paper trail is your evidence. It's what you show the regulator or the assessment body. There are probably 4 foundational documents you'll always see.
Okay, number 1.
First, you absolutely need an HF integration plan. This is the roadmap. It sets out how HFI will be done across the project, the scope, the resources, the methods, the timelines.
Got it. What's next?
Second, the HF issues register. This is a living document, really crucial. It tracks every single identified human factor, problem, or potential issue, what the proposed fix is, and its current status: open, closed, in progress.
Like a snag list, but for human factors.
Exactly like that. Third, the big one, the comprehensive HF assurance report. This synthesizes all the analysis, all the V&V results, the issue resolutions. It basically summarizes the overall safety evidence related to human interaction for the safety case.
And the last piece.
And finally, you need the detailed verification validation reports. These provide the specific proof that every derived HF requirement, like that maximum allowable cognitive workload we talked about, was actually tested, met, and validated successfully in the final design that's going into service. Okay, so now we move from those broad principles and life cycle stages into the hard engineering tools. We have to use specific technical methodologies to actually quantify the human element, assign risk values.
This is where it gets really technical. It seems almost counterintuitive, doesn't it? Applying statistics to something as variable as human behavior. How on earth do you quantify the probability of human error?
It does seem counterintuitive, but we use a structured approach called Human Reliability Assessment, or HRA.
HRA, okay.
This is a systematic, often statistical analysis used to quantify the probability of human errors happening under specific operating conditions. HRA isn't just pulling a number out of thin air, though.
Yeah.
No, it uses established, recognized techniques. Things like THERP, that's the technique for human error rate prediction, or maybe HART, the human error assessment and reduction technique. There are others, too.
And how do these techniques work?
They generally break down complex tasks into smaller, discrete subtasks or steps. And then, crucially, they factor in what we call performance shaping factors, or PSFs.
Performance shaping factors, what are those?
PSFs are the contextual elements that influence performance. Things like time stress, is the operator rushed? Environmental quality, is it noisy, poorly lit? The quality training, the quality procedures, and critically, the quality of the interface design itself.
So if the lighting is bad or the operator's under huge time pressure, the PSF basically says the error probability goes up.
Exactly. Each PSF is weighted based on how much it's likely to degrade or improve performance for that specific subtask. The data generated from this, a quantified human error probability, or HEP, is absolutely vital.
Why vital?
Because it guides design improvements in a measurable way. Let's say through HRA, we find out the HEP for a critical emergency isolation task is $10 to $12. That's a 1 in 100 chance of error each time it's performed.
Okay.
But maybe the safety case for the whole system demands that task reliability be $10 and $1,000. Well, that HRA result tells us we must redesign something: the interface, the procedure, the training, until we can demonstrate through reassessment that the HEP meets the safety target. It forces engineering rigor onto the human interaction piece.
That makes sense. It gives you a target to aim for. And doing that, HRA properly relies on really knowing the tasks inside out, right? Including the specific ways people might mess up.
Absolutely. Which is where task and usability analysis comes in, often using specific error taxonomies.
Taxonomies, like classification systems.
Precisely. Task analysis, as we mentioned, maps every operator action and identifies potential failure points, especially focusing on cognitive load. Where might the operator get overwhelmed?
And the taxonomy helps categorize the errors.
Yes. A key method, particularly if you're dealing with complex control systems or signaling systems, is applying detailed error taxonomies. A well-known one is a Sherpa.
Sherpa.
Yeah, it stands for Error Classification System for Human Error Reduction and Performance Assessment. It's quite detailed. A Sherpa, in similar taxonomies, force us to categorize what kind of error it was. Was it a slip, a lapse, or mistake?
Okay, hold on. Slip, lapse, mistake.
Yeah.
What's the difference? Aren't they all just errors?
They are all errors. But the underlying cause is different, which means the fix is different. A slip is basically an action error. You intended to do the right thing, like press button A, but you accidentally press button B right next to it. Your execution failed.
Okay, like a typo when typing.
Exactly. A lapse is more of a memory failure. You forgot to perform a required step in a sequence. The plan was correct, but you missed a part.
Right.
A mistake is different. It's a planning error. The operator fundamentally misunderstands the situation or misinterprets the system's state and therefore forms the wrong intention or plan of action entirely. They then execute that flawed plan perfectly.
Ah, I see. So the action might be flawless, but the thinking behind it was wrong.
Precisely. And this classification is critical because the solution for fixing slips, maybe better button spacing, clearer feedback, is totally different from fixing mistakes, which might need better training, clearer procedures, or improved displays to enhance situational awareness.
That's a really important distinction. Now, beyond the cognitive side, the thinking and memory, there's the physical interaction. The term ergonomic design gets thrown around, sometimes sounds a bit generic.
It shouldn't sound generic.
But you're saying it's pure applied science, using things like anthropometric data.
Absolutely. Ergonomics, or human factors engineering as it's sometimes called, is the scientific study of designing systems and interfaces to optimize human well-being and overall system performance. It's highly scientific.
How so?
We use anthropometric data extensively. That's the statistical measurement of human body sizes, reach, strength across different populations. We use this data to optimize, say, a train cab layout.
Give me an example.
Okay, we might use anthropometry to ensure that, say, 95% of the intended operator population from the 5th percentile female to the 95th percentile male can comfortably reach a critical emergency brake handle without excessive stretching or awkward posture.
Right.
Or we'd use biomechanical data to ensure the resistance on a control lever is within optimal limits enough to prevent accidental activation and give good tactile feedback, but not so high it causes fatigue over a long shift. It's amazing when you think about it. We're taking statistical averages from thousands of human bodies just to decide that the handle should be exactly, say, 3 centimeters wide. That's where the science gets really tangible.
That's fascinating. Okay, so when we talk about how HFI fits into the bigger picture of whale safety, preventing accidents,
Yeah.
that classic model always comes up, the Swiss cheese model.
Ah, yes. James Reason's model. It's still the essential analogy for contextualizing risk, I think.
How does HFI relate to the cheese slices?
Well, the Swiss cheese model illustrates that catastrophic failures usually only happen when the holes in multiple layers of defense, the slices of cheese, momentarily align, allowing a hazard to pass right through. HFI is fundamentally about strengthening the slices related to human performance, making the holes smaller or less likely to align. In rail, you might have one slice representing technical system reliability, signal integrity, track condition.
Right.
The next slice is maybe operational procedures, the rule book, the training. And a third slice, often, historically, the thinnest one is the human factor defense layer. Things like good workload management, clear interface design, fatigue management.
So HFI shores up that human slice.
Exactly.
Okay.
HFI is dedicated to ensuring that slice is robust. So even if there's a latent technical weakness, a hole in one slice, a strong human procedure or an ergonomic design acts as buffer, preventing those holes from aligning and stopping an incident before it happens. #Tag4, standards and regulatory frameworks.
Okay, this is really critical for our audience, especially those working in or entering the industry. HFI isn't just a good idea, a recommendation, or an internal best practice. It's mandatory, right? It's codified in serious international engineering standards. It forms the bedrock of modern rail safety regimes.
Absolutely, 100%. It's not optional. The foundation for railway HFI, particularly in Europe but influential globally, is underpinned by key international standards, mainly from CNELAC and sometimes IEC.
Which ones should people know?
Well, the most foundational standard covering the entire safety lifecycle for railway applications is EN 501126-1. That deals with RAM's reliability, availability, maintainability, and safety.
The RAMS standard.
Okay. And EN 50126 doesn't just vaguely mention competency. It explicitly mandates the identification and systematic management of specific human factors throughout the entire RAM's lifecycle. It puts the responsibility squarely on the systems engineer and the project to provide rigorous evidence about the operator's role, capabilities, and limitations within the system.
So it's baked into the core safety lifecycle standard. Are there others focused more on the technology itself, especially safety-critical electronics?
Yes, definitely. You have EN 50129, which applies specifically to safety-related electronic systems for signaling. It prescribes detailed process frameworks for how you must manage human factors within the design, development, and validation of that safety-critical hardware and software.
Okay.
And similarly, IEC 61508 The generic functional safety standard, which influences many sectors, including rail, requires comprehensive HF considerations. This is especially true when you're dealing with systems related to a specific safety integrity level, or SIL.
Right, SIL. We hear that acronym constantly in safety engineering. For those maybe newer to the field, can you just quickly explain the fundamental concept behind safety integrity level, and why does HFI compliance affect it so deeply?
Sure. SI stands for Safety Integrity Level. It's basically a discrete level, usually running from SELF 1 up to SEL 4, which defines the required level of risk reduction that needs to be provided by a safety function.
So higher SIL means more critical.
Yes, exactly. A SEL 4 system, the highest level, requires extremely stringent design and validation measures to ensure its probability of failing dangerously is incredibly low, near zero. Now think about HFI's impact.
Okay.
If you design a complex automated train protection system, say, to meet SL4 requirements technically, but the human interface for operating it or overriding it in an emergency is confusing, poorly tested, or induces high workload, well, that human interaction introduces significant failure potential. It basically compromises the entire SIL rating you were aiming for.
So the human element can drag down the overall integrity.
Absolutely. You can think of it like this. Achieving SL4 technically is like securing a valuable asset behind 4 incredibly strong, independent technical locks. HFI ensures that the human operator has one simple, intuitive, reliable key to operate those 4 locks correctly every single time. If the key is confusing or easy to use incorrectly under pressure, the whole system fails its integrity requirement, no matter how strong the individual locks are.
That's a great analogy. And these standards, EN 50126, 50129, IEC 61508, they aren't just European documents, are they? They're backed by powerful regulatory bodies, worldwide setting performance benchmarks.
That's right. You see this global alignment, or at least strong influence, from the FRA, the Federal Railroad Administration of the USA, and the ERA, the European Union Agency for Railways, across to the RSSB in the UK, and ONAN-RSR in Australia.
And beyond.
And this standardization is really key for global rail development. For instance, in rapidly developing rail markets, like those in the Middle East governed by the GCC rail authorities, they often adopt or very closely follow these ERA-aligned CENELEC frameworks, especially where specific local guidance might still be developing.
So it shows the widespread transferability.
Exactly. It shows these fundamental HFI principles are globally relevant, and we're increasingly speaking a common regulatory language when it comes to proving safety, including the human aspect.
Okay, this structure of standards and compliance leads us straight into what feels like a crucial professional dilemma. One that engineers, safety managers probably wrestle with constantly. The difference between compliance versus genuine risk-based HF management.
Ah, yes. This is a really important point, almost a philosophical dividing line in the safety profession sometimes.
How so?
The question is, does strict adherence to the letter of the standards, methodically checking all the boxes listed in EN 50126 Annex E for human factors, does that truly guarantee safety?
Some might argue it does, right? If you meet the standards.
Some organizations definitely operate that way. They see proving compliance as the end goal. Job done. But true, deep safety culture requires adopting more profound risk-based frameworks. Frameworks that go beyond just the documented processes and try to address those trickier, often undocumented cultural factors, behavioral norms, cognitive biases, things that can't easily be captured in a simple compliance checklist.
So compliance might not be enough.
Over-reliance on simple compliance is arguably the single greatest recognized pitfall in system safety assurance today, across many industries, not just rail. It can create a dangerous false sense of security. We must be pushing towards implementing comprehensive, risk-based human reliability analysis tailored to the specific operational context, not just settling for meeting minimum standard requirements. #Tag5. Real-world case studies and safety metrics.
Okay, to pull this out of the standards, documents, and the theoretical frameworks, let's look at the real world. Let's talk about specific case studies where rigorous HFI was put into practice and had measurable results. Our first example focuses on personnel protection in what sounds like a very high-risk environment. The Doha Metro Depot Safety Project in Qatar.
Yes, depots are inherently high risk. You have multiple trains moving, often automatically or remotely, in close proximity to maintenance staff who need to be on or near the tracks.
What was the specific problem in Doha?
The initial risk assessment identified a high frequency of personnel needing access to tracks within the depot for maintenance, coupled with the potentially catastrophic consequence of any inadvertent or unauthorized vehicle movement into an occupied work zone.
So people and moving trains in the same space, how do they tackle that using HFI?
Their solution involved implementing a sophisticated depot personnel protection system, or DPPS. The specific technology they used involved RFID-based zones.
RFID, like tags, how did that work?
Right. The HFI team first did very detailed task analyses. They studied exactly when, where, and crucially how personnel might accidentally walk onto a live track or perhaps fail to properly secure a track section before starting work. Based on that understanding of the human error modes,
Hmm.
the RFID system was designed. It created dynamic, electronically controlled work zones. Essentially, when a worker carrying an authorized RFID tag entered a designated track zone, the system automatically inhibited any train movements into that specific zone, either physically through points control or electronically via the signaling system.
So it created a safe bubble around the worker.
Effectively, yes. A virtual safe zone, enforced by technology, but designed around the predicted human behaviors and potential errors. And the result was really striking.
What happened?
It basically eliminated human factor incidents related to personnel access errors in the maintenance areas, reduced them to near zero. And critically, proving this system's safety and reliability actually supported an ahead-of-schedule opening for the depot because the safety case was so strong.
Wow. And is that kind of system transferable?
Oh, highly transferable. We've seen very similar technologies like the Zone Green DPPS, for example, successfully deployed in depots across the UK and Australia, achieving similar significant reductions in human error risks during maintenance. It's a proven HFI solution for that specific hazardous environment.
Okay, great example. Our second case study involves high-frequency, very complex operations, the Dubai Metro's human-machine interface design. Now, this system is famous for being driverless, relying entirely on centralized human monitoring and control.
That's right. Driverless systems are, in many ways, the ultimate stress test for centralized HMI design and the supporting HFI processes.
Why?
Because while the trains run automatically, the system's overall performance, safety, and recovery from disruption depend entirely on the human operators in the Operational Control Center, the OCC. Dubai Metro runs with incredibly tight headways, sometimes down to 2.5 minutes between trains.
That's incredibly frequent.
It is. The operators in the OCC are managing the traffic flow, they're intervening during any degraded modes or failures, and they have to make potentially high-stakes decisions under considerable time pressure. Their success is fundamentally rooted in rigorous HMI design and the associated HF training.
How was the HMI designed with HFI in mind?
The interfaces were meticulously designed to minimize cognitive stacking, having too much information presented at once, and to prevent mode confusion, which is a common source of error in complex automated systems. Things like clear visual hierarchies, consistent interaction logic, effective alarms.
And the outcome.
This dedication to HF and the OCC helps eliminate shift-related timing errors, ensures smooth service regulation, and maintains the system's impressive punctuality. It really proves that even when the human isn't physically driving the train, their interface with the automated system must be optimized using HFI principles to prevent critical failures.
Okay, those are powerful examples. Let's ground this conversation now in some broader safety data. If HFI is genuinely working across the industry, we should be seeing the results in the measurable safety metrics, right?
We should, yes, but we have to look quite closely, and the global picture is complex.
How so?
Well, for instance, while overall rail safety has improved dramatically over the long term, some recent global data, like for 2023, actually showed a bit of a worrying rise in the number of significant accidents compared to the previous few years, potentially reversing a downward trend.
That doesn't sound great.
It's not ideal. However, interestingly, even with more accidents, the overall global safety index actually showed a slight improvement,
How does that work?
primarily because there were fewer victims per incident. This suggests that while we might still be having incidents, perhaps our post-incident response, crashworthiness, and emergency management, which also involve human factors, by the way, are getting better at mitigating the consequences. But the challenge remains eliminating the root causes, many of which are HF-related.
Okay, so a mixed picture globally, but is the progress clearer if we look specifically at human factor-related incidents, particularly in regions with strong HFI focus, like the U.S.?
Yes, I think the U.S. rail data, particularly looking at recent figures like for 2024, shows where systematic HFI efforts really seem to be paying off. The overall train accident rate there is down significantly year over year, around 15%, and impressively down about 33% since the mid-2000s.
That's substantial progress.
It is. But crucially, if you drill down to the cause codes, incidents specifically attributed to human factors saw an even sharper reduction, down about 18% just compared to the previous year's data.
Wow, 18% reduction in human factor incidents in 1 year.
Yes, it's a strong signal. It strongly suggests that the focused investment in proactive HFI programs, better HRA, targeted training modifications, maybe fatigue management programs, it's having a direct, measurable impact on operational safety performance. It helps prove that the human element, while complex, can be reliably managed with the right scientific approach.
That's encouraging. However, there's still one area where the human element remains, tragically, the most persistent and devastating challenge, isn't there? The public interface.
Ah, yes. This is the constant, heartbreaking challenge for the entire industry globally. Over 95% of all rail-related fatalities worldwide involve either collisions at level crossings or people trespassing on the tracks.
That statistic is just staggering.
It really is, and it underscores that HFI's focus has to extend beyond just the trained professional operator in the cab or the control center. It must intensely focus on public interface design.
What does that mean in practice?
It means designing physical environments, fences, barriers, station layouts that passively discourage trespassing. It means using technology intelligently to detect intrusions and warn the public. And it means proactive, continuous community outreach and education campaigns. We are essentially applying human factors science to try and manage the behavior of untrained, often distracted, and highly variable system users, the general public. It's a huge ongoing challenge. #Tech6. Emerging trends and professional challenges.
Okay, looking ahead now, HFI isn't static. It has to evolve rapidly, especially with all the digitalization and the relentless push towards more automation in rail. We're seeing huge shifts in control centers, aren't we? Particularly with advanced digital human-machine interfaces.
Absolutely. This transformation demands really intensive HF oversight. We're moving away from those big physical mimic boards and fixed panels.
Yeah, the wall of lights.
Exactly. Towards highly dynamic, often touchscreen-based consoles with adaptive displays. The information presented can change based on the situation.
That sounds powerful, but also potentially confusing.
That's the risk.
Mhm.
The challenge for HFI is ensuring these adaptive interfaces, while definitely powerful, don't inadvertently lead to cognitive overload or mode confusion for the operator. HFI focuses on designing these screens to actively reduce operator errors, especially in complex environments like automatic train control ATC centers.
How?
By doing things like prioritizing critical information dynamically, ensuring absolute consistency in interaction logic regardless of the system state, using color and layout very carefully to guide attention. Making complexity manageable, essentially.
And technology isn't just changing the interfaces, it's offering new ways to tackle those two biggest safety headaches we mentioned: human error by staff and public trespassing. Let's talk about AI and maybe augmented reality.
Right, two huge areas. AI-enhanced monitoring is becoming a real game changer for that public interface challenge, particularly trespassing.
How is AI being used there?
We're seeing AI-powered video analytics systems being deployed, especially around complex infrastructure sites or construction interfaces with the public. These systems can analyze camera feeds in real time to detect potential trespass intrusions much more reliably and quickly than human monitoring alone. Some systems are achieving over 80% accuracy in predicting and preventing trespass incidents before they happen.
So AI handles the repetitive watching.
Yes, it leverages AI for high-volume visual monitoring, freeing up human controllers to focus on verification and intervention when the AI flags a potential issue. On the training side, augmented reality, AR, training is really starting to transform cognitive readiness for operators.
AR, how does that work for training?
Instead of just reading manuals or doing classroom exercises, AR allows operators to overlay digital information onto the real world or immerse themselves in highly realistic simulated environments. You can simulate rare, high-consequence emergency scenarios, things you could never practice safely in reality, like a complex equipment failure or a station evacuation under pressure.
So it feels more real.
Much more real. It dramatically improves their decision-making skills, their procedural memory, and crucially, their ability to manage stress and perform correctly when the unexpected actually occurs on the job.
But these rapid advancements, AI, AR, more automation, they surely introduce new, complex HFI challenges themselves, particularly around automation dependency.
Oh, absolutely. This is possibly the most critical long-term HF challenge the industry faces right now. How do we balance the undeniable benefits of rapid automation, maybe even fully driverless systems, against the inherent risk of reduced operator vigilance and skill degradation?
The complacency factor.
Exactly. If the technology becomes too reliable, too smooth, the human operator can become complacent. They transition from actively monitoring to passively observing, and then their core skills, Their ability to diagnose a novel failure, something the automation wasn't programmed for, their ability to take over smoothly and effectively in a crisis, those skills can actually degrade over time from lack of practice.
So what's the HFI solution to that?
HFI has to focus on designing the entire socio-technical system to counteract this. That might involve implementing specific skill maintenance protocols, maybe requiring operators to periodically handle certain situations manually, even if the automation could do it, designing interfaces that keep the operator in the loop mentally, not just physically present. The goal is to ensure the human remains a competent, vigilant supervisor, capable of handling the unexpected rather than just a passive spectator whose skills atrophy.
That's a tricky balance to strike. And finally, thinking about the profession itself, is there a challenge facing the entire industry that actually inhibits learning and improvement in HFI?
Yes, I think there is. It's the issue of data fragmentation.
Meaning,
Effective global benchmarking, knowing if your organization's or your region's safety performance, especially regarding human factors, is truly world-class or just average. It's currently really hampered by fragmented HF data reporting.
different systems, different definitions.
Exactly. Different regional regulators, different private operators, they often collect and categorize human factors data from incidents and near misses in slightly different ways. There's no single, universally agreed, detailed taxonomy used everywhere.
And that stops us learning.
It impedes learning maximally from every event. To really achieve global safety excellence and share best practices effectively, we urgently need more standardized, more comprehensive, and definitely more collaborative data collection, and sharing specifically focused on the human factors involved in incidents. #tag7. Practical takeaways for the learner.
Wow, okay, that's a huge amount of technical detail, regulatory context, future trends. Let's try and distill this down now. Let's transition to some really practical, actionable advice. For our engineering students listening, for those early career professionals just entering this critical field, if you take just one single thing away from this entire deep dive today, what should it be?
Okay, the number one lesson. The one that saves, projects millions of dollars, and, more importantly, prevents tragic errors down the line. Prioritize early integration. Get HFI thinking in early. You absolutely must proactively push to integrate human factors requirements and considerations right from the very concept phase of any project.
Why is that so critical?
Because the most common, most costly pitfall is treating HFI as an afterthought. Oh, we'll get the HF guys to look at it just before deployment. That guarantees siloed activities, missed hazard modes that should have been designed out earlier, and potentially incredibly expensive late-stage redesigns when you find out operators can't actually use the system safely or efficiently.
So get HFI specialists involved right when the project scope and system requirements are being defined.
Yes, at the requirement stage. That's non-negotiable for complex systems.
Okay, lesson 1, integrate early. Now, given the multidisciplinary nature you described, psychology, ergonomics, engineering, what specific skills should people try to cultivate now to be really competitive and effective in this space?
That's a great question. My advice would be actively work to cultivate multidisciplinary skills. Don't just stay siloed in your core engineering discipline.
Branch out.
Yes. Find ways to blend that deep technical knowledge, whether it's software, mechanical, electrical, with at least an introductory understanding of cognitive psychology principles, human-machine interface design guidelines, and basic ergonomics.
Why is that blend so important?
Because the best, most effective HFI professionals are bilingual, in a sense. They can speak the language of engineering requirements, validation, risk probabilities, and the language of the human sciences workload, situation awareness, usability heuristics. You need to be credible in both worlds to bridge that gap effectively. You need to be able to talk about failure rates and perception in the same meeting, maybe even the same sentence.
Makes sense. Okay, so you're on a new project, or maybe you're asked to audit an existing system from an HF perspective. How do you make sure you cover all the bases? How do you ensure comprehensive coverage of all the relevant HF factors without missing something crucial?
Don't try to reinvent the wheel every time. Use structured checklists and frameworks. Leverage the existing standards-based frameworks that we talked about.
Like EN 50126.
Exactly. Like the specific human factors considerations listed within the EN 50126 RAMS framework, or maybe the ACE or ASB requirements in Australia, or relevant sections of IEC 61508. These documents, while sometimes dense, provide a comprehensive, systematic starting point for coverage. They prompt you to consider things you might otherwise forget, like training independence, maintainer competency, environmental conditions, procedural clarity. Use them as your initial checklist.
Okay, use the standards as a guide. Now, moving from the requirements on paper to the actual deployment. What's the key practical step there?
Always pilot and iterate. Theory and simulation are essential, but they aren't reality. The only truly reliable way to validate your HFI design success is to get prototypes, mock-ups, or early versions of the system into realistic, high-fidelity environments.
And test with real users.
And rigorously collect feedback from representative operators actually trying to use it to perform realistic tasks.
Yeah.
Then, and this is the crucial part, use that feedback for design refinement before the final system gets rolled out across the network. Remember, HFI isn't usually a one-and-done design process. It often requires continuous validation and iteration against the messy reality of human use.
Pilot, test, iterate. Got it. Okay, to wrap up this advice section, what is the single biggest pitfall, the main thing you want to warn the next generation of railway engineers and safety professionals against doing when it comes to HFI?
Avoid at all costs an over-reliance on simple compliance. Do not let yourself or your organization fall into the trap of thinking that just meeting the minimum requirements stated in a standard is automatically equivalent to achieving genuine safety.
The box-ticking mentality.
Exactly. That box-ticking mentality is dangerous. Instead, you must always strive to adopt that deeper risk-based approach we discussed. Rely on comprehensive human reliability analysis, tailored to your specific context, to truly understand, assess, and mitigate human-related risk rather than just checking boxes on a generic form. Be risk-driven, not just compliance-driven. Hashtag outro. So as we close out this deep dive, maybe let's just reiterate that core message one last time. Railway safety is maybe the perfect definition of an intricate socio-technical system. It's not just tech, it's people in tech. And because of that, the focus in design and operations in assessment must permanently shift beyond just the rails, the wires, the signals, the software, to the person interacting with all of it.
Yeah.
That person, the driver, the controller, the maintainer, even the passenger, is the most adaptable component in the whole network. But also, if overlooked or poorly supported, potentially the most vulnerable. Safety is an integrated property of the whole system, human included.
That leaves us with a really interesting, maybe provocative thought to mull over as we finish. Given this relentless rise of AI, more automation, ever smarter systems, how can future rail system designers ensure that, while the technology is taking over more and more of the routine tasks, the operator's critical skills, especially their ability to handle the truly unexpected failure, the anomaly the designers didn't foresee, how do we ensure those skills remain sharp and integrated?
Instead of being degraded by automation dependency.
Exactly. How do we design a system where the human operator remains the ultimate master of the situation, the resilient backstop, not merely a passive spectator waiting for something to go wrong?
That is the challenge for the next decade. And perhaps a practical way to start thinking about it is to encourage you, the listener, to explore concepts like the human factors evaluation framework. Think about factors like competency, attitude, motivation, workload. And really consider, how would you quantify those? How would you build requirements around them right alongside your technical parameters like latency or bandwidth in your next design project?
Integrating the human metrics with the technical ones from the start.
That's the future, I believe, of truly safe, efficient, and reliable rail travel.
Fantastic insight. A huge thank you for sharing your expertise today. And thank you all for joining us for this deep dive into the human side of rail safety. We look forward to continuing the conversation next time.
Thanks for listening to Safe Tracks, the System Safety Assurance podcast. Here, we talk all about how safety assurance keeps our railways running safely, smoothly, and reliably every single day. If you're curious about RAM management, RAM analysis, and how reliability is actually calculated, check out the RAM's Ready podcast playlist on this channel. It's packed with great insights. And hey, don't forget to subscribe and tap the notification bell so you'll know the moment a new episode is out. Until next time, stay safe, stay assured.